you, Alex. Good morning and welcome to Scale Transform. My name is Brad Porter and I'm Chief Technologist at Scale AI. What an amazing lineup today, and we're incredibly excited to get started. We're particularly pleased to kick off today's Transform 2021 with Dr. Andrew Ng. Andrew is one of the most impactful educators, researchers, innovators, and thought leaders in the field of artificial intelligence. He's also the founder of Deep Learning AI, a general partner at AI Fund, as well as an adjunct professor at Stanford University. Andrew's courses on AI, machine learning, and deep learning are some of the most popular on Coursera and have helped countless engineers and developers break into the field of AI. Today, Andrew will be giving a presentation followed by a fireside chat discussion with our CEO, Alex. Please join me in welcoming Andrew to Transform.
Thank you for having me at this Scale AI conference. Today, I'd like to share with you some ideas I think will be important for how we build AI systems in the future. And in particular, I hope to share with you some thoughts on how I think our mindset should shift from building big data to building good data. And this will unlock how we can more efficiently build AI systems for many more industries, especially ones outside consumer internet. But first, let's take a snapshot of where we are in the AI industry. I think AI is one of the major inflection points of technology that we've seen in the last several decades. There was the mainframe and mini computer revolution in the 1960s, then the PC revolution, the internet revolution, the mobile client revolution, and I think the AI revolution is still underway. Whereas the earlier technology revolutions disrupted many major industries, maybe more and more as time went on, I think AI is on the path to disrupt every industry. And we're still in the early stages of that. Further, many of the fundamental drivers that had caused AI to take off in the last decade are still continuing to drive forward progress. Take the falling costs of compute. It's almost as if there was an old Moore's law in the pre-GPU era, and then there's a new Moore's law, but the rise of compute is continuing unabated. The world continues to become more and more digital, and this is creating data, and there continues to be new algorithms invented, like very literally every week. Let's dive a little bit more into these. Take compute. One of the diagrams that's inspired me for quite some time is this benchmark that was created by the Stanford Dawn Bench project, which showed that the cost to train an ImageNet to a relatively high level of accuracy fell from over $2,000 to about $10 in just about a year. If you look at the rising language model sizes, leading research groups are also continuing to build bigger and bigger models. And so compute continues to become more and more available. And on the research front, the number of research papers published in AI continues to take off like never before. So the compute, digitalization of our world, and the creativity of researchers continues to drive forward AI progress. But what challenges still remain? I've been saying for many years now that AI is the new electricity. Similar to the rise of electricity starting about 100 years ago, which transformed every industry, AI will do the same. But if you look at what AI has done so far, it has transformed the software internet industry, especially the consumer software internet industry. So web search, online advertising, language translation, social media, these businesses have become much more effective and valuable because of AI. But once you look outside the software industry, everything from manufacturing to agriculture to healthcare to logistics, I think AI today is still in the earliest stage of development. But I think that in the future, AI applications outside consumer internet will be even bigger than the applications we have in consumer internet. Sometimes working in tech is easy to forget that the majority of the economy is actually not in the software consumer internet industry. So I hope AI will go to those other industries and have an even greater impact than we've seen so far. Why are we there yet? And why is building AI systems still hard today for so many industries? I think it would be useful as we build AI projects to more systematically think about the life cycle of a machine learning project, the life cycle of an AI project. There's been a lot of attention in academia, in research, and in the popular press about building AI models, such as training a supervised learning model that can input an English sentence and output a French sentence, or input this and output that. But and training models is something that AI, deep learning, has gotten much better at over the last decade. So that's something that we should absolutely celebrate. But those of us that have built and shipped commercial systems know that there's a lot more to building an AI system other than training the model. When I work with AI teams, I encourage teams to think about the entire life cycle of a machine learning project, which includes starting with scoping the project, defining what's worth working on, what projects to pursue. Turns out to be one of the hardest skills still in today's AI world. Next is collecting the data. This includes defining what is the data you want, making sure the inputs X are representative, making sure the labels Y are unambiguous, to then training the model, carrying out error analysis, and iteratively improving the model by updating the model, or in many cases, getting more data until your model performs well enough. And then deploying in production. Some teams view deploying in production as the endpoint of an AI project. I don't view that. I don't view it that way. I think often deploying production only means you're about halfway there, and only after you've deployed in production do you then get the live data to flow back to your system to continue to learn and to improve and refine the AI system. So for many teams today, I should tell them that when you deploy in production, you're only maybe halfway there. And that's why I think when you look at the lifecycle of machine learning project, this is a very iterative process where when you're training the model, you often want to go back to collect more data. And even after you've deployed the model, you may want to train the model to update it or go back and update your data set. So many teams will collect some data, train a model, and when you get through that for the first time, you have what we sometimes call a proof of concept, like a demo, maybe a prototype that does well on test sets, that's stored in a data store somewhere. But after you've deployed in production, there is still an iterative process to go back to the early stages to keep on improving the system. In terms of why building AI systems is hard, I think building the initial proof of concept is hard, especially when there's insufficient high quality data. And you never have enough high quality data, so that makes building POCs hard. But even after building a successful proof of concept, there's often still a gap between the proof of concept and production. So let me step through both of these issues in a little bit more detail. It turns out that AI had grown up in consumer internet companies that may have hundreds of millions or like over 1 billion users. And when you have 1 billion users, that gives you a huge data set, and it's great. You should use that data to learn from it. But once you look outside consumer internet, many industries just do not have these giant data sets. For example, I do a lot of work on manufacturing visual inspection, and fortunately, no manufacturing plant has manufactured 1 million, or heaven forbid, 1 billion scratched smartphones that would need to be thrown away. So if you want to use computer vision to see if a smartphone is scratched, no one has 1 million pictures of distinct scratched smartphones. Or take healthcare. Work on many healthcare problems where we may only have 100 X-rays of a patient with a certain condition. And so your ability to get an AI system to work with only 100 images or 1,000 images is key to breaking open these application areas. And so I have been surprised myself at how often it is possible when you do certain things that it becomes possible to build a computer vision system, not with 1 million images like with ImageNet, but with mere 100 images or maybe a few hundred images. And this small data capability and technology, and frankly, not just technology, but practices and ways of thinking, will be important for expanding AI into these other industries that may not have giant data sets. Let me give you an example. It turns out that if you have a small data set like this, so I used to fly drones, helicopters and drones, and if you want to predict the RPM of a motor as a function of the voltage, if you have 5 examples and it's a noisy data set like this, it's really difficult to fit a good function, right? Just, any number of curves could fit this data set. Um, Now, if your data set is noisy, but you have a lot of data, then it's actually okay. With a curve like this, you can, relatively confidently fit a straight line, take a local average, or you do just fine. One very interesting case is what if you have a small data set? So 5 examples, same with the example on the left, but the examples are relatively noiseless or low noise. In this case, even though you have a very small data set, the clean and consistent labels allows you to fit a function that does quite well. I think big data is great. If you can get it, let's use it. But even when you have small data sets, I've found that putting an emphasis on good data hygiene practices can have a huge impact on the quality of learning algorithm of model you can fit. And even today, I'm surprised over and over, at how we can build systems that work with 100 images or sometimes even fewer. At the highest level, an AI system is made up of code plus data. Where by code, I mean code including your choice of model or your choice of machine learning algorithm. And we as the AI community have put a lot of work into inventing new practices and algorithms and ways of improving the code. And I think the amount of work on improving the data should grow as well. In fact, we tell jokes, well, we say it like it's a joke that 80% of data science is data cleaning. We say it like it's a joke, but well, it's kind of a joke, but it's also true. And to me, if we find that 80% of machine learning engineers' work or 80% of the data scientists' work is data cleaning, then maybe data cleaning is well, it has to be a core part of the work of a data scientist or machine learning engineer. When I speak with general audiences, I sometimes use the analogy data is food for AI. And the goal in life is not to maximize the number of calories. And beyond a certain point, it's about having high quality food. And so today, we have to spend a lot of time sourcing, preparing high quality data before we train the model. And I think that just like a chef, would spend a lot of time to source and prepare high quality ingredients before they cook the meal, I feel like a lot of the emphasis of the work on AI should shift towards systematic data preparation. Recently I went into Archive and looked up the 100 most recent machine learning papers that I found on Archive, and I just skimmed the abstracts. It's very informal, skimming of abstracts. And I found of the 100 papers whose abstracts I skimmed, 99 were on machine learning models, and literally one was on data augmentation. So maybe arguably, for a very loose sample, 99% of the research work, of academic work, is on 20% of the work of building these AI systems. One idea I want to share with you is the idea of data iteration instead of model iteration. Today, many research teams will hold the dataset fixed and iterate to try to improve on the model. I've found that this is a great way to do research. Download a benchmark dataset, improve performance, maybe publish a paper if you succeed. For most of the commercial projects I work on, I've actually often gone to the team to say, hey, everyone, the model is just fine. It's good enough. Use RetinInit or ResNet or UNet or some neural network. It's just good enough. But instead, I've gone to my teams to say, please hold the code fixed. Let's not mess with the code anymore. And let's just iterate on the data to get the performance we need for this application. And for quite a lot of the projects I've worked on where I gave that direction to the team, it actually accelerated the team's progress. I think one of the challenges we have is today, a lot of how we iteratively improve on the data is often, some engineer or a few engineers hacking around in a Jupyter notebook rather than a repeatable systematic process and moving toward making the data more systematic and repeatable rather than having engineers, hack around until hopefully they have the right insight. That I think will accelerate the development of many machine learning systems. I've talked about the importance of data in the context of small data projects where the data set is smaller, in which case having really clean labels helps. I want to share with you that this also holds true for big data problems, which are long tail problems. So specifically, if you're working on web search, which has lots of rare queries, so the rare queries, you actually have only a small sample of, even if you have a giant data set in the aggregate. Or if you're working on self-driving cars, where you have to handle the very rare corner cases, right? At one time, that pedestrian does something unusual. Rare corner cases in self-driving car, even though the self-driving car industry in aggregate has a very large data set, the number of examples you have for the rare corner cases is actually very small. Or product recommendations. Even if a company sells a lot of products, you also have things like the cold start problem, products that haven't been much sold yet, or the long tail items where you may not have a lot of data on. Even for those, even if the data set in aggregate is huge, there are many small data problems embedded in this big data problem. And I think that more systematic data practices for getting very clean data will still be critical for improving performance on these otherwise big data problems. So building the proof of concept is hard when you don't have enough data. You never have enough data. And one of the directions I hope a few can get better in is to think about tools for systematically improving our data sets to drive machine learning progress, in addition to thinking about how to improve our models to drive machine learning process. And just for the record, for those of you that are highly technical engineers, hyperparameter search is important. You do have to get the hyperparameters chosen reasonably, but in many projects I see, once you've chosen a reasonable choice of hyperparameters, then often iterating on the data will buy you at least as much progress as spending comparable amounts of time. So searching for the latest state-of-the-art algorithm and downloading that and trying that out instead. And again, AI world is very diverse, so your mileage may vary. And the advice I'm giving is more for commercial projects than for doing brand new research projects. Even after you've built a proof of concepts, we still often have a proof of concept to production gap. So Accenture recently released a report saying that many companies' AI projects are still in the proof of concept stage. So why is that? There was a very influential paper by Dave Scully and others out of Google that pointed out that of all the code needed to build an AI system, only a relatively small portion is machine learning code. And unfortunately, building a working system often requires more than doing well on your holdout test set. For example, a lot of teams have published research papers like this. This is work that my collaborators and I were involved in. But work that says AI detects pathologies, at a level comparable to human radiologists, right? And so, even though there are research results like these, if you take an X-ray today, chances are there's not going to be an AI system reading your X-ray. So why is this? I think one major reason is that a POC result that works according to published paper often does not work that in a production setting because of concept drift and data drift. So it turns out if we collect data from Stanford Hospital with high-end X-ray machines, well-trained technicians, and test on very similar data, then we can indeed publish papers showing that we are comparable or sometimes superior to human radiologists. But if you take that data set, if you take that neural network that you just published a paper about, walk it down the street to an older hospital with slightly older X-ray machine, maybe a different protocol that the X-ray technician uses to image the patient, maybe the patient's at tilted angle, then the performance degrades significantly in a way that is much less true compared to a human radiologist that could walk down the street from Stanford Hospital to a different hospital and do just fine. And this is why I think deployment is a process, not an event. And beginning deployment only marks the beginning of flowing data back to enable continuous learning. One of the things I'm most excited about is the rise of MLOps as a discipline to help us make building and deploying machine learning systems more repeatable and systematic. In the traditional software engineering world, we would write code, maybe software engineers would write code and then hand it off, gently hand it off to the DevOps team that were responsible for ensuring quality and infrastructure and deployment. With AI, where we now have not just code, but close with data, I think we need a new discipline, maybe called MLOps, to help make the creation and deployment of AI systems more systematic. If you look online, you find different inconsistent definitions for what MLOps is. Even large companies have definitions of MLOps on their webpage that will differ than each other. So this is an exciting emerging discipline. Let me share some thoughts on that. One of the challenges with AI software is that it is not a linear process. So in traditional software, you could scope it, write the code, hand it over to DevOps, and then deploy it in production. But with AI software, that doesn't work, right? Because you scope it, collect data, train the model, deploy in production, and then the process is iterative. You have to keep on coming back to the earlier stages of the process. So that's why I think for most projects, it is a mistake to think of MLOps as a team that you hand your model to for them to deploy and then they take care of it from then on. Instead, I think MLOps needs to support multiple stages in the lifecycle of an AI project because there isn't this smooth handoff. Because even post-deployment, you have to keep on collecting data and keep on updating your model. In the projects that I work on, I often think of MLOps as supporting all the stages, really, especially collect data, train model, and deploy in production, all of these stages of an AI project. And I feel like there are a lot of things that MLOps needs to do: manage data governance, ensure the data systems are reasonably fair, maybe audit performance, ensure scalability of the system. So a lot of things that MLOps needs to do. So in terms of deciding what's the single most important thing an MLOps team needs to do, I think it should be to ensure consistently high quality data throughout all stages of the machine learning project lifecycle. There are other things MLOps can do as well, but if they do only that one thing, then that will significantly accelerate the creation and deployment of AI systems. So to any of you that are standing up MLOps teams, I would urge you to have those teams consider this as the number one principle that they must do well to organize their work around, and they could certainly do other things as well. Just to summarize, as AI systems are code plus data, for many projects, not all, but for many short-term commercial applications, I think the code is, almost a solved problem. Download an open source thing on GitHub, it'll do fine. Not for all problems, but for many problems. But the data is a huge unsolved problem. And I think having a shift in mindset from big data to good data, coming with practices to develop good data will be critical for accelerating the build out of AI systems for many industries outside consumer internet. So what is good data? Has to cover the important cases, good input distribution X, has accurate labels, so high quality Y. The data is timely feedback from deployment to manage data-driven concept drift. And of course, we need good governance of this data to be reasonably free from bias, to ensure fairness, satisfies privacy, data provenance and lineage, and regulatory requirements. And if we can stand up MLOps teams as an industry to help solve this issue for us, then I hope we can accelerate the adoption of AI, both in consumer internet and perhaps even more important, outside consumer internet. Thank you.
Andrew, really enjoyed your talk.
No, thanks for having me here, Alex.
In your talk, you discussed what good data entails and why that's so important. Could you speak through some of the implications of bad data?
Even today, I've been sometimes surprised at how much you could do with a surprisingly small data set, so long as the data set is clean and consistently defined and well labeled. Maybe, for example, take speech recognition, build several speech recognition algorithms. And if you're working on speech recognition for voice search, you may get an audio clip where someone says, today's weather, right? So question is, how do you transcribe that? Is it comma today's weather, or dot today's weather, or is just noise? So you just don't want to transcribe noise, you should just transcribe today's weather. It turns out any of those three ways of labeling your data is just fine. I would probably pick the first or the second, not the third. But any of them, will work well enough. But the problem is if you have a lot of labelers and one third of your labelers choose the first way, one third choose the second way, one third chooses the third way, and then you have noisy data in the learning algorithm, just as to randomly guess which one of these transcriptions one of your labelers happen to pick, which is very difficult for a learning algorithm. So I've been surprised how many times if you go through error analysis of a machine learning problem, it turns out that there's a problem with the input X or with the definition of the labels Y, or sometimes the data is stale. It's just not the timely data because you didn't deploy and close the loop. And fixing those issues, well-defined representative input X, well-defined and accurate label Y, and timely data. If you could do these things, then sometimes fixing these things is even more important, necessary than having a giant data set. Although, of course, you can get a giant data set. We should totally do that too.
How can organizations working on AI ensure that the data that they're working on is so-called good, and what kinds of investments should they be making to ensure that this is the case?
One thing I mentioned in the talk is a lot of teams, partly because of the way AI research is done, tend to hold the dataset fixed and iterate on the code. But I think we should, for many problems, also consider holding the code fixed and iterating on the data. Now, how we do this is still quite ad hoc across the AI industry. Is often you have some engineers, hacking around in the Jupyter notebook, and hopefully the right engineer has the right insight that allows you to improve your data in the right way. I do see that senior AI engineers often have a framework for doing this more systematically. I've seen, for example, when my senior friends and I look at a project, we often give advice to teams. They're actually very similar to each other. So there is a methodology. But I think this methodology is still a little bit folk wisdom in the heads of a relatively small group of senior AI people. Very high level. Things I do include systematic error analysis, look at the ways the algorithm isn't quite working yet, and then tag the different error clauses. And now, instead of asking, how can I improve my code to solve the problem, consider asking, how can I improve my data to solve the problem? Maybe one example to connect speech recognition. I've built speech systems before and then found that they don't do well if the speaker is, there's a lot of car noise in the background, right? So if you're doing voice search in a car, don't do that if you're driving. With the passenger seat, a lot of background noise, speech system doesn't work well. One thing you could do is say, well, how can I, adjust the algorithm to make it do better? That could work. The other solution is to say, let's just use data augmentation or collection or something else. Let's get a lot more data of what people sound like in cars. Now, I have done that. My friends have done that in a reasonably systematic way. But I think developing process and ways of thinking will help the AI world move forward faster.
Andrew, it's so great to hear you talk about the importance of data when it comes to building these machine learning systems. Some people, such as Andre Karpathy, have gone even so far to say how data is really what does the programming in these machine learning systems, not the code. And in some sense, data is kind of the new code. How do you think about the right proportion of investment and effort that organizations should spend with data versus code?
It's very problem dependent. There are definitely cutting edge projects where we just need better algorithms. But I find that for a lot of commercial projects, the AI field is so broad now, it's hard to give one size fits all answers. But I find that for a lot of commercial applications, if your goal is to build something and just make it work, then very often the code is basically a solved problem. There'll be some open source GitHub thing that's appropriate license, just download and use. Still need to tweak it, fit in the framework. But for a lot of computer vision problems, for example, if your data set is small, then a modern neural network is a low bias learning algorithm. It's such a high variance, low bias learning algorithm. If you have only thousands of examples, then modern neural networks will fit your training set just fine. And there, the vast majority of the effort, if we put it into the data, I think that often leads to faster improvement. So I think I mentioned at the top, I often go to teams and say, ask the teams, hey everyone, code's good enough. Please stop messing with the code. The only thing we'll do for this project is work on the data to get the performance we need. And I've been surprised how many times when I give that direction to the team, it results in faster progress. But again, not everything in the AI world is one size fits all because the field is now so diverse. But I do think that as a field, we should shift more of our mindset to engineering the data as opposed to primarily engineering the code.
One of the things that's super interesting about your experiences, Andrew, is that you've worked on such a range of problems, everywhere from speech transcription at consumer internet companies to self-driving cars to now more recently manufacturing. Over a time horizon of 20 to 30 years, what are the industries that you think will be most deeply impacted by AI? And what are use cases that you're particularly excited about?
All of them. I have to say, I think having led AI teams in a couple of very large consumer internet companies, a lot of my focus now is on trying to take AI to all of the other industries outside of consumer internet. But so I'm excited about manufacturing, agriculture, healthcare, logistics, also e-com, retail. I think there are a lot of industries that do not have 1 billion users per company, so much smaller data sets. But where we can develop AI tools, it will enable us to create a lot of value. Most of the economy is not consumer internet, and I think AI still has a room to grow to make inroads there. Right now, landing AI does a lot of work in computer vision, specifically manufacturing visual inspection. So something manufactured by a factory, can you help build a computer vision system to inspect it, to see if there's a scratch on a smartphone or a crosswire on a semiconductor wafer or a dent in automotive components or what have you. I'll share one interesting design pattern that we use in manufacturing that's useful for many industries though, which is that one of the challenges that the AI world faces is the cost of customization. So every factory, sort of makes something different. And the neural network for detecting scratches on smartphones is not particularly useful for detecting cross wires on a semiconductor wafer. It's not that useful for detecting dents in an automotive part. So how can one roll out AI solutions to 10,000 factories unless, without hiring 10,000 machine learning engineers to do all the customization work? And Jason Horowitz had a very thoughtful article talking about one of the challenges of AI being the high cost of customization. And that has made some parts of AI like the SaaS business, but with lower margins. So who wants to do that, right? Who wants to say, let's build a SaaS business, but with lower margins because of the cost of customization, which is per customer. I think the only way out of this dilemma for the AI industry is for us to build vertical platforms to enable industry experts in these different industrial domains, in these different organizations that want to use AI to do the customization themselves. So rather than me trying to hire 10,000 machine engineers to build a custom AI model for every factory, I find a more promising path forward. This is what we do with Landing Lens, to build a tool that enables the factory to do their own customization. And I think when we build tools that are transparent and empower the plant operators, in this country in Asia to update the model any time of day they want, then they can do the customization and can deploy and operate these AI tools with much more confidence. I think this design pattern of building vertical platforms will be important for other industries as well. Take electronic health records. Every hospital, every healthcare system, has a slightly different way of storing patient data and coding their electronic health records. So if you want to build AI for reading EHRs, which I've done before, how do you deploy this to 10,000 hospitals without hiring 10,000 machine learning engineers? Again, I think that the way out of this is to build a vertical platform that enables every hospital, every healthcare system to do the customization they need to make the AI work for their healthcare system. So I think this design pattern will be useful for a lot of industries.
So Andrew, you bring up this super interesting point of customization. One of the big advancements that's happened in the field over the past year is transformers, which have really standardized most of the neural network architecture code for machine learning algorithms. How close do you think we are to a world where most of the customizations actually come in the form of data customizations versus code customizations?
I think for a lot of industries, it will be possible to pick one model that will work for that use case. So for manufacturing visual inspection, right, RetinaNet or UNet, seems just fine. There is still integration needed. The pre-processing, the output of the AI system needs to be integrated to the manufacturing plant. There is that customization needed. But other than that, a lot of the further customization is indeed in making sure you find the right data to feed to the learning algorithm. Or take EHR, maybe come up with some algorithm, right? That will be good enough. Maybe XGBoost, some flavor of boosted decision trees for dealing with electronic health records. There's still the integration in the pipeline, right? What do you do when the AI system outputs a notification that you should consider this drug for this patient or consider this consultation for this patient? There's that integration that's needed. But again, I think a lot of this will be to think through the entire life cycle of a machine learning project and to collect the data, train the model, and then deploy and close the loop to enable continuous learning to make sure that the healthcare system, whatever is the application, can manage their own AI system. When the data set is small, then a lot of modern learning algorithms are actually low bias algorithms. But when we have a high variance problem, then figuring out the right data is often a promising thing to work on in order to adjust that.
For folks that are in businesses or industries where they're now trying to implement AI and have that impact their products and their businesses, what are some skills or frameworks that product managers, engineers, or business leaders should know or learn about so they can be maximally successful?
AI adoption is so complex, it's hard to distill it down into a couple bullet points. I actually wrote and published online a doc called the AI Transformation Playbook that synthesizes a lot of the lessons I had learned, leading AI teams and speaking with CEOs on how a corporation can adopt AI. So the AI Transformation Playbook. I think just a couple ideas. I think that many enterprises would be well served to start small. When I was leading the Google Brain team, at that time, a lot of people were skeptical about AI, and people didn't know how to use modern deep learning. This is a state in a lot of industries today still. So my first internal customer within Google was the speech recognition team, where my team worked with the speech team to help make speech recognition more accurate. And it wasn't the most important project in Google. It wasn't web search or online advertising. But by delivering that nice initial win, it then opened the door for me to start a bigger project with the Maps team, where we use OCR basically to read house numbers in Google Street View to more accurately geolocate buildings and homes in Google Maps, improve the quality of map data. And only after making that second project work could I then start a more serious conversation with the advertising team, that then clearly has a much more direct revenue impact. So I think is many organizations are encouraged to start quickly, but it's okay to start small and then plan for the organization to learn and then ramp up the capabilities. I still remember, you'd be surprised to hear, I still remember our first GPU server at Google. It was just a server under some guy's desk, right, with a nest of wires. And that stupid server taught a lot of us how to operate GPUs in a multi-user environments and how to use them for deep learning. And then, and then now it looks like, right, a lot of GPUs around many companies, but that turned out to be, for my team, a key step. The other thing that's very difficult for a lot of companies is scoping. I think, there's still a global shortage of machine learning engineers, not enough, especially experienced machine learning engineers. But there's one role that's even harder to hire for than machine learning engineer, which is the AI architect. So having someone that can understand the business problem, understand the technology, and form a point of view on what can and cannot be done, what's the ROI, and select the one or a small handful of projects that's worth doing, that is still very challenging. But I find that when the business leaders are willing to learn a little bit about AI, and when the AI tech people learn a little bit about the business, often that cross-functional brainstorming process could lead to a healthy project selection. Hey, I'm curious, Alex, you've helped many companies start to think about AI. What do you see in terms of best practices of helping companies transition to AI?
Andrew, it's a super interesting question. There's 3 points I would kind of make. I think the first one is, like you described, I think actually this on-ramp of problems is very important. I think it's important that organizations tackle problems that are important for their business, but also tractable with machine learning. I think all too often it's very easy for organizations to consider some big vision, such as fully automating customer support, without identifying the right roadmap of smaller problems along the way that allow the organization to build the muscle in AI and build a core competence in the technology before jumping all the way to the big vision. And so having this sort of steady roadmap of problems, I think, is really important. The second thing I would say is solving problems where the organizations already have the data to be able to work on the problem. It's very hard to be able to do machine learning, like you know as well, in contexts where you don't have any of the data, and businesses naturally have some pools of useful data or some pools of data which are going to be efficient to label. And I think it's important to start with problems where that's the case, so you can move quickly. And the last point that I would make is that I actually think we're at a very different point in AI maturity today, where for most businesses and most industries, the set of problems that you can attack with AI and machine learning, and the set of problems that are tractable, I actually think it's possible to just sort of follow where the industry is going. And so I think that gives organizations a blueprint and a roadmap to be able to work on problems where it might be known that the problem is tractable. So for example, areas like customer support automation, or predictive maintenance, or being able to do AI for defect detection. These are use cases which are becoming more and more normalized, and some organizations are able to be successful with them. And so it makes it much easier to apply AI. You don't need to be a genius. You don't need to have a lot of ingenuity in approaching the problems.
On the there being data piece, that's a very good point. I've met some CEOs and sometimes CIOs that have said to me things like, "Hey Andrew, give me 2 years, maybe 3 years max, to upgrade my IT infrastructure. And then in 3 years, we'll have this beautiful IT infrastructure with all the data you could possibly want, and then we'll do AI then." And I would say, I think that's a mistake. Much better to look at the applications that are a little bit more AI ready, with some data. And I don't think anyone in the world has perfect data infrastructure. What I find is that every company looks at their data infrastructure and they go, "Boy, my data is so messy. I bet other companies are better organized than me." But it turns out everyone says that. And I find it's better usually to start from the data you have, and we all feel like our data could be less messy, more clean, more complete. Start with the data you have, quickly try to leverage it using AI, and then the feedback from the AI team will be incredibly useful for prioritizing where to build out the data infrastructure. So, in a manufacturing plant, do you want to upgrade the sensor to collect data 10 times a second rather than merely 1 time per second? It's only after you're in the AI project can you do that. Or for a self-driving car, do you want to add another camera here or another camera there or LiDAR there? Only when you have cars driving on the road, well, it's really helpful for helping an engineering team make that decision. So I think some projects are more AI ready, and those are often good candidates for the quick initial wins to then ratchet up progress from there.
For the next generation of people who are going to be shaping the world of AI, many of whom are in our audience today, what's one piece of advice you would give them to take to heart to be maximally impactful for the good of the world?
Maybe I'll share 2 thoughts. One is keep learning. And I find that the AI world is so vast today. There's so much knowledge that one's success is often more related to someone learning a little bit every week for a long time. And so, turns out if you read 2 research papers a week, it's quite a lot of work to read 2 research papers a week, then you have read 100 papers a year. And that actually is a very significant body of knowledge. So I would say, keep learning. And the second is, in addition to, studying and learning, also do project work. There was someone I spoke with at a company, at a travel company, and they had done this project building a chatbot. I won't describe the details, but they told me that the management team told them, look, this chatbot has very low ROI. I don't see the revenue case. Why are you doing this? And I felt that was actually a pretty bad thing for the management chain to say, basically shut it down. Because I find that doing projects is an important part of everyone's learning experience. And yes, of course, we would love to do the project with a high ROI. And when you have a good AI architect, you have better chance of doing that. But for individual learning, is often fine. Not if you do this forever for the rest of your life, but if you start with some projects, and that's a key part of your learning experience as well. And and I think also, unfortunately, there is a gap between academic research, AI, and what it takes to build these things into production. So I find it very useful to nudge teams to think about not just the model training, but the entire life cycle of an AI project, from scoping, collecting the data, to building the model, to then deploying, and just gaining practice with everything in the life cycle of a machine learning project.
Andrew, it was so great having you. Thank you so much for being here at Scale Transform. Hearing your thoughts about how AI is going to transform industries, what the bottlenecks are, and what the bottlenecks on the data are, have been incredibly insightful. Thank you again.
Okay, awesome. Thanks for having me, Alex. It's been great fun to join you here.